Assalamualaikum warahmatullahi wabarakatuh. Thank you for having me in this conference. I would like to show the presentation of our research with the title Experimental Studies of Application Passive Momentum Exchange Impact Damper (PMID) on UAV's landing gear. Background of this research is the landing gear is the part of the aircraft that receives the most significant shock load during landing. This is due to the magnitude of the maximum acceleration of the landing gear vibration when experiencing shock load. This phenomenon causes the landing gear damage due to excessive vibration. Therefore, uncontrolled shock load can damage the landing gear structure and even pierce its frame structure. The momentum transfer method was applied to landing gear design to reduce the maximum acceleration amplitude of the vibration due to experiencing shock load during landing. The basic working principles of the PMID is from the MID momentum transfer. When the collision occurs between the first pendulum and the second pendulum, the first pendulum momentum and kinetic energy have transferred to the second pendulum. The same condition apply to the collision that occur between the second pendulum and the third pendulum. We can conclude the momentum and kinetic energy in the first pendulum as transferred to the third pendulum. This energy and momentum transfer mechanism cause the second pendulum to be maintained in a stable condition. In designing a landing gear system using PMID, the first pendulum is analogous to the shock load excitation force. The second pendulum is analogous to the main system in the form of U-profile spring, and the third pendulum is analogous to the mass of the PMID system. The working of the principle of PMID on landing gear, the PMID landing gear mechanism, which is considered to have linear rigidity. When the landing mat and collision, momentum and kinetic energy on the wall were transferred to a U-shaped lip spring. The same thing happen to U proper, the second mass, because the U proper and the second mass are contact with each other. When the collision occurs, momentum the proper kinetics energy. U proper is transferred to the second mass. Is in the contrast to the three pendulums swing principle. When the collision occurs due to the shock load, the U proper experiences and the deflection because the lip spring have stiffness. The transfer of energy and momentum in the landing gear can be maximized by design a U spring with linear stiffness and low deflection. In the second mass, a spring is attached, which gives the second mass the tendency to the move because the personal frequencies influence it's due to the stiffness and the second mass influence quickly. The contact spring stiffness value determine the contact time between the U profile and the second mass. The amount of energy and momentum transfer was determined by value of the second mass used. Methodology of the research, we define 5 processes. The first one, we designed the landing gear mainspring, use the U profile. And the second one, we designed the PMID shock absorber system. The third one, we make the test instrument based on the design. The fourth one, the test the design to see PMID system performance on the landing gear. Tests are carried for several parameter configuration of the mass of the contact spring and excitation force magnitude. And the last one, we test the result, and the result are then analysis and compare with design contact mass configuration. The result of the research, we use the finite element simulation method and model analysis showing the figure. The calculation of the frequency and model coordinate determined by applying the 4 lowest nose landing gear modes was obtained from the simulation. See the lowest mode simulation result on the nose landing gear, the form U profile, where the lowest occur the first personal frequencies of the system at 47 Hz, the value first frequency in the simulation, then use parameter for testing personal frequency experimentally. The result of experiment testing that have been carried provide the lowest 4-mode value for nose landing gear system. The first one, 51.5 Hz. The second one, 85.5 Hz. The third one, 98.5 Hz. And the last one, 109.5 Hz. The U-profile landing gear strut nose element model when applied loading. Based on the simulation result, it's often the U-profile spring stiffness is 194.9 Newton per meter. The U-profile spring stiffness value used as a comparison with the stiffness of the experimental result. The experimental result of the FRF graph as parameter in determining the first personal frequency of the landing gear system. The first personal frequency value from the experiment is the 51.5 S. Test result without the PMID system. It can be analyzed the maximum acceleration amplitude value of the nose landing gear in the form of the U-profile spring is around 170 meter per second square. For the test result with the PMID system, with the mass contact, PMID mass contact 120 per gram, the mean of the maximum acceleration amplitude is the 144.9 meter per second square. For PMID mass contact 120 65 gram. The mean maximum acceleration amplitude of the contact mass is the 130.5 meter per square second square. For the PMID mass contact 185 gram, the average maximum acceleration amplitude is the 128.5 meter second square. The comparison result of the landing gear shock response without PMID proper and PMID landing gear, the decrease of the response of the maximum acceleration amplitude of the vibration of the mass variation of the 125 gram is the 13.86%. The mass variation of the 165 gram resulted in decrease 22.41%. The mass of 185 gram and decrease of 23.06%. This result explains the PMID method effectively reduce the shock load of the nose landing gear. The conclusion of the research it as often experimental model of shock vibration control with passive momentum change method in unmanned aircraft landing gear, which can reduce shock vibration response by up to 23.06%. It found the comparison of the shock vibration response in landing gear structure without the damper as higher maximum acceleration amplitude respondent landing gear structure with passive momentum change damper. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.